In this video, we're going to look at Maxwell's equations. We're going to start by going back to Faraday's law and look at kind of some of the interesting bits that implies. And then we'll talk about Maxwell's equations and specifically why Maxwell gets all this credit when we haven't talked to him about him at all yet this year. So going back to Faraday's law, right? This is kind of the summary. If you have a piece of metal, right, a copper ring, something like that, a wire, what have you, in a magnetic field, we know that there's an EMF induced equal to the rate of change of magnetic flux. And Lenz's law says that will have this negative sign. It will be in the direction opposite of, that will induce a flux in the opposite direction of the change. And so, oops, I went backwards. If there is current, then there has to be an electric field inside the ring that's pushing the charges, which is an interesting idea. We've said, an EMF is induced, it pushes charge around, but we hadn't said previously that this has to be due to an electric field, because we know that inside of a conductor, when everything's in a static situation, the electric field is zero inside and no charge moves. We also have said that electric field lines go from positive to negative charge. But of course, here, there's no 2 points. There's an electric field kind of pushing the charge around everywhere. And so that here, the electric field lines is a nice circular path of electric field, because there's no single positive and negative starting and ending point. Because this electric field is not created by a separation of charge like the electric field in electrostatics. It is created by a changing magnetic field. And these electric field lines aren't just inside that wire where we can observe their effect. They're actually everywhere. So it turns out that you can kind of expand our understanding of Faraday's law to say this rate of change of magnetic flux is actually not just equal to an EMF, but it's equal to a potential difference that could be seen as the closed integral of E dot dl. And so this is kind of going back and thinking about, well, how does electric field and electric potential relate to each other? And this is the way. And so now if you put all of that together, we have something really interesting. It says a changing magnetic field will actually generate an electric field. And so if we think about a solenoid, and a solenoid is a great example because it has a pretty uniform electric field, or magnetic field, in the middle. And we've sort of observed that the magnetic field inside is quite strong, and the one outside is very, very small, right? And so when we think about that, we can think about, well, then what is the electric field inside the solenoid and outside the solenoid, right? So let's think about this, right? If it has a radius given, E dot dl is equal to the change in magnetic flux. We got a couple of R's here. The R's involved are the area of the line around which we're traveling for our electric field calculation, our E dot dl. That's the circumference of that circle. And the R here, the pi r squared, is of course the area inside whatever region we defined. And so those are indeed, one R value. And we can find that we get some electric field in volts per meter, right? That is how this works. And hopefully that makes sense, right? We have electric field times a distance, right? A circumference is equal to our change in magnetic flux. So that's how that actually comes together. So what's different here? Well, if you go outside of that, now the R's are no longer the same, right? Inside, those two R's were the same. Outside, they're not. And what we end up with is here, right? Inside, we've got a magnetic or an electric field. Outside, we've got an electric field that involves a different amount of kind of enclosed area. The last thing to do then is to combine all this stuff together into Maxwell's equations. This is James Clerk Maxwell. And he took 4 fundamental equations about electric fields and magnetic fields. And his big contribution was that he kind of combined them all together and saw their interconnected relationships. All right. And he added one small piece. So the first thing is Gauss's law. We've learned this one, right? The electric field in a region is generated by some charge. We can use this Gaussian surface. If we enclose charge, we can figure out the electric field. The net electric flux through a closed surface is proportional to Q enclosed. That's the big idea for Gauss's law. Faraday's law, which we just added the last piece to, essentially says that a changing magnetic flux generates an electric field, right? And that causes an EMF that can push charge around. The other thing that we've mentioned before, but haven't really spent much time on because it basically was our way of saying you can't have a single north or south pole, was Gauss's law for magnetic fields. It says that the closed surface integral over any Gaussian surface of B dot dA is zero, meaning that there is no way to enclose a magnetic charge, for lack of a better word. You can't have a magnetic, what we call monopole. You can't have a north pole or a south pole apart from the other. So whenever you split a magnet, you always still have a north and a south pole. And this is all based on the consequence that magnetic fields are generated by a moving charge, not point charges. Then we came up with Ampere's law, or Ampere did. Rather, we talked about this, the idea that if you enclose current, you can talk about the magnetic field strength using these things called Amperian loops, which are similar to Gaussian surfaces in that they enclose something that we care about. And so we have Maxwell's equations with one small piece missing. But we've got all of these things. And so we've got enclosed charge, static charge generates electric fields. You can't enclose single poles for magnetism, so you can't have a magnetic field because of that. Faraday's law tells us how we get moving charge to generate electric field, and Ampere's law tells us that you get, a change in magnetic field gives us an electric field. That's Faraday's law. And Ampere's law says moving charge generates magnetic fields, right? That's what they say. But Maxwell thought, well, changing magnetic flux induces an electric field. Is it possible that a changing electric flux would induce a magnetic field? Basically, if you were to vary currents, change the electric field, change potentials in some way, could you generate a magnetic field? And we already knew that moving charge did, and it turns out that he was correct, right? That you can get a magnetic field to be generated by changing the electric flux. And so this was added to Ampere's law and said, well, it's not just charge or current enclosed. It could also just be a changing electric field, which is kind of interesting, that generates a magnetic field. So you can either have a constant flow of current, of charge, or you can have a changing electric field or electric flux that will generate a magnetic field. And this led to something really exciting, right? This displacement current, this thing that happens when you change electric flux that generates a magnetic field, allows you to say some interesting things about situations we already know about, right? If you think of a parallel plate capacitor, we'll use a circular one here because the area is kind of simple and it matches with what we've been doing. As the capacitor charges up, the electric field is increasing. And what it does is it creates this magnetic field. And so if there's electric flux between the plates that is changing, right, not just a static one, but as it's building up, it induces a magnetic field that's going around in a circle like that, right? And it circles in a region between the capacitor plates. The B field behaves as if the current was flowing through the capacitor, which is kind of interesting, right? We said that it doesn't actually do that, but the B field inside is very similar to, it basically gives you the same thing as if there were just a straight wire going through, which is pretty cool. So why does Maxwell get all this credit for all this stuff? Well, the big idea is he didn't just figure out the displacement current. What he did is he kind of surmised that something that was observed in one way could work in the other, and then he put that together and kind of thought about the consequences. He said, if changing magnetic field induces electric field, and changing electric field can induce a magnetic field, and changing magnetic field can induce an electric field, and changing electric field can induce a magnetic field, and so on and so forth over and over and over again, then can they make waves? I didn't need to make myself bigger when I said that, but it's kind of fun. And if so, how fast are they? It turns out that if you combine all this together, you find out that a changing magnetic and electric fields, that changing one changes the other and becomes what's called self-propagating through space. Those waves travel at the speed of light. And the speed of light is 1 over the square root of those two constants that we've been looking at for a while, mu naught and epsilon naught, which is actually really exciting. So electromagnetic waves, all you got to do is wiggle a charged particle. If you've ever had an antenna, there aren't as many antennas that are just long pieces of metal, but you've certainly seen one, an antenna from an older style, maybe AM/FM radio. Um, that thing is just letting electric fields move charge up and down in it, and that's how it receives the signal. The transmitter, a big antenna on the other side, if you've ever seen them, there's several of them near the highway as you're driving around in Massachusetts along 95, 128. Big towers, 4 of them in a row. I think they're television antennas, but they basically send a signal, charged particles up and down, to generate an electric field that generates a magnetic field, and then that magnetic field generates an electric field, and it travels through space. And this is essentially what it looks like. You can imagine generating either one of these, but usually we think of generating the electric field because it's easy to imagine that. You just move charged particles around, and you can get electric fields that are changing. But of course, we also know that moving charged particles generates, or changing, that's basically a current, so you get a magnetic field as well. And they propagate like this. They're orthogonal to one another, or mutually perpendicular. One is vibrating or oscillating in the XY plane, the other in the XZ plane. And this is why he gets credit, right? Because one, he combined everything together to give us kind of a complete understanding of how electricity and magnetism are related. And he showed that light could be an electromagnetic wave, and all of the sort of optics stuff using waves that had been done, thinking about reflection and refraction, sending light through off mirrors and through prisms and that kind of stuff, was now connected to electricity and magnetism. And that's why it's kind of a big deal. So what we've done all of this stuff, right? All of these different things in electricity and magnetism we can put together now. And some of them together, not the force part, but everything else, is essentially what Maxwell did. All right. We're almost done. Very exciting.